Okay, last session of the day. Thank you for joining me. My name is V32 Gutterman, and this is a joint work with Benny Pincus from Haifa University and Tzachi Reinman from the Hebrew University of Jerusalem. Just a short bio about myself. I'm the Chief Technology Officer and co-founder of SafeEnd, and a lecturer at the Hebrew University and the Interdisciplinary Center at Herzliya. In the last 10 years, I was doing research in the different fields of applied crypto and applied security. And just a few words about SafeEnd. We do endpoint security for the non-TCP IP port. These are the USB, FireWire, Bluetooth, and so on. And this talk is, of course, about something else, about the Linux random number generator. And actually, there isn't a better place to speak about random number generators than a casino. You all know the importance of randomness when playing in a casino. But actually, not only in casino. Almost every security protocol that we know or use needs random number generators. SSL, TCP sequence numbers, DNS, SSH, and many, many other security protocols use random number generators. Usually we are familiar with the term Alice picks a key K at random. That's from the basic cryptography course. And of course, if this key isn't so random, then the entire security system can easily be broken. Two examples, one from 10 years ago, very famous one, the Netscape SSL. David Wagner and Ian Goldberg were able to find that the Netscape SSL was using a weak PRNG. And in the next slide, I'm going to show this PRNG, the source code. And last year, we were able to mount another attack on Apache session IDs. So we were able to guess your session IDs, which should be random. And using that attack, we were able to enter to someone else's session ID, steal a session ID. And just to make sure that everyone follows me, here's the Netscape source code for using the random number generator. So you can see at the bottom of the slide, the key is created completely from the random number generator. It's supposed to be strong. It's supposed to be 128 bits or 60 bits. But if the random number generator isn't random enough, if the space is smaller, like 20 bits, 15 bits, 10 bits, then the entire system collapses. That's it. But that brings us into a problem. When speaking about computers and random, that's not a good combination, because computers are very deterministic. So how random number generators are implemented? Usually using some kind of state. We have some state, we seed it in the beginning, and then we get an endless stream of bits, which should be, again, random. But what's random? Usually two meanings. One, pseudo-randomness, meaning that if an adversary takes the output stream and read it, there is no easy way to trace back from the stream of bits back into the states. If there was an easy way, we could easily predict the next bits. A second important property that we usually seek in cryptography and in security systems is once we break into the machine, we don't want to be able to trace back past secrets or past keys. That's called forward security. The fact that once we break in, the history remains okay, remains secure. In the recent years, we were having an advance in PRNGs, and we started using PRNGs with entropy. We used the different noise coming from the operating system to feed the PRNG. And all over my talk, I'm going to use the word entropy, and I mean system noise, hard disk movements, the different interrupts, memory allocations, and so on and so forth. So we have the same PRNG, but we keep feeding it with additional entropy each couple of minutes, seconds, depends of course of the level of entropy that we can gain. And what can we achieve from this kind of security? First, we should have, of course, the two previous properties. That is the pseudo-randomness and the forward security. But in addition, we gain another property. That's the backward security. What we gain is using the new entropy, the new unpredictable bits coming from the operating system, the fact that if an adversary is penetrating the system and getting the state of the PRNG, there is a limited time that he or she can use it. Because after limited time, after a very short period, there is enough entropy coming into the system and the state is clear again. So that's the advance of using entropy for pseudo-random number generators. Okay? And that's a good reason. We can make sure that even if someone is penetrating to our system, there is a very limited influence to this penetration. You can steal the state of the PRNG, but that's for a very limited time. And actually, most modern operating systems are using such entropy-based pseudo-random number generator. That's another scheme to describe it. We describe the state, and we move from one state to a new state, plot some output, and using the entropy, compute the next state. So I described shortly what are PRNGs, entropy-based PRNGs. I'll get into a few examples of using these entropy-based PRNGs in modern operating systems. And then in my second part of the talk, I'm going to get in details to Linux. Most of our research was doing reverse engineering for the Linux pseudo-random number generator, the one at the kernel, the dev random and the dev urandom, and I'm going to describe our results. And you're going to see that it isn't so easy, even though you may say to yourself, well, it's open source. What kind of reverse engineering was needed there? And you'll see in a couple of minutes. And we were able to use this information, this analysis, for a couple of attacks. One of them is simple denial of service. One of them is more theoretical, because the number of computation is very, very high. That's in the general case. That's the forward security cryptanalysis. But there are several cases where our attack is very, very practical. And one such example is the wireless routers, such as the OpenWRT. These are the home routers running Linux, and I'm going to demonstrate that we can easily break almost any security protocol running on this platform. So that's a very serious vulnerability right now, and I hope it will be fixed in the near future. We also did some entropy, some noise measurements for some Linux machines, and that's it. So PRNGs, there are lots of constructions of entropy-based PRNGs. I guess that most of you are familiar with the ones like the PGP, that ones that tells us to type something on our keyboards, to move the mouse. There are others like Yarrow, RSA, and so on, but all of them are using some ad hoc structures. Take your data, mix it, hash it, use it to encrypt, use all sorts of tools, but no proof is provided whether this is secured or not. Some of it is also used for operating systems besides Linux. One of them is BSD, which using Yarrow together with embedded AES. And of course, I mentioned Linux. There are also some implementation for Unix. And I forgot one operating system, a small one, Windows. There is an embedded entropy-based pseudo-random generator called crypt-gen-random. And I guess that if you were implementing some security protocol for Windows, you probably use this one. Your SSL, your Internet Explorer, by default uses this function. What do we know about it today? Nothing. Microsoft published about two pages in the MSDN saying it's very secured. It is using the entropy collected from the system, and that's it. I was able to find, there is a patent that Microsoft filed about it, but the patent doesn't reveal any too much. And we started, actually we are working on doing the reverse engineering and see how secure this system is. Maybe something for next year. There is a new result from last year, a new theoretic academic result from Boaz Barak and Shai Halevi. That's from CCS, that's an academic convention that provide the framework for entropy-based PRNGs. It's a good framework using some stable structures that can use to prove both forward, backward, and pseudo-randomness. Unfortunately, it's a new paper, and none of the PRNGs is using this structure. So if you are going to implement a new system, considering using an entropy-based PRNG, please consider using this scheme. It is very easy to implement. You can just take AES together with some hash function, and you'll get these properties, the three properties that I mentioned in the beginning. Okay, now to Linux. The entropy-based PRNG is implemented in the kernel. It's a product that started by Theodor Tso. That's his picture. He was a student at the time at MIT, 1994. So it's about 12 years now. And it's a very, very complex entropy-based PRNG. Lots of patches over the years, complex structures, changes in a weekly basis by many people. We were able to see from the CVS, from the CVS repository logs, that for 18 months, or yes, about 18 months, this PRNG had a huge bug where instead of reading n bytes, the PRNG was reading 4 times n bytes. You didn't get a blue screen because that's part of the kernel, and you don't have blue screens in Linux, of course. But actually, the mathematical functionality was wrong, very wrong. And it's critical. It is used by many, many security applications by default in Linux, including TCP, PGP, SMIME, SSL. If you're running a web server on Linux, that's the PRNG you're most likely to use. Regarding functionality, there are two interfaces, one in the kernel and one for users. The one for the kernel is called getRandomBytes. That's a C function, which is used by any kernel function who needs random bytes. For example, the TCP sequence numbers are using this function. If you are implementing an application, whether you are a user or administrator, you probably are using one of two device drivers, dev random or dev urandom. That's your two options. And you can see here the definition of the writers, of the implementers of this entropy-based PRNG. The difference between them is they both use the same entropy, but dev random should be much more secure, whereas dev urandom is less secure, but is much faster. So kind of the instruction, if you read the manual, if you need extremely secure bits, use dev random. The penalty will be that you may be delayed till there is enough noise, enough entropy in the system. And if you're willing to give up some level of security, then use dev urandom, which works much faster. Actually, I'm going to show you in the next slide that it's not like that. There is no real difference between them. The entropy collection mechanism isn't correlated in the right way, unfortunately. So to implement this, there is a counter called entropy estimation, which measures how many different bits of entropy came from the operating system, entered the pool, the entropy pool, and whenever you extract, this counter is decreased. So whenever the system adds entropy, the counter gets increased. Whenever you consume, it decreased. Very simple. And for dev random, if this number gets to 0, you go to sleep. Your process goes to sleep till there is new entropy. For dev urandom, you get data forever. So that's the mechanism in very, very simple. I mentioned, and that's the last line of the slide, that actually there isn't a good relationship in the implementation. Actually, there isn't a good relationship between the entropy coming in and the entropy which you get. So actually, the pool can stand for a minute on 0. You can sleep, your process can sleep. You will be waiting for additional entropy to come. The entropy will come and will be entering some point of the pool, and then you will get entropy, but from another spot in the pool. So there is no real relation, just the counter, but the entropy comes from a different space. I mentioned, and when we first published it, I got lots of flames about our result. What kind of reverse engineering is it? That's not reverse engineering at all. The code is there for you. That's so great about open source. I have nothing against open source. I think open source is great. But on the other hand, open source doesn't prove that things are secure. That's it. It doesn't prove. The fact that it was there for 12 years, okay. It isn't easy to read. It's about 2,500 lines of code, which is very, very complex to understand. It includes lots of mathematics, lots of complex changes, unfortunately some bugs, and reverse engineering, and as someone said in the early talk this morning, is not about reading the code. Some of us can read assembler very, very fast. It's about understanding what's the functionality of a module. So unfortunately, this wasn't an easy task. And someone asked me earlier, we were working on this one for more than a year. Also, because of the fact that it is part of the kernel, debugging and working with the kernel was a very complex task. And whenever you add changes, of course, to the kernel, you also influence some of your measurements, and that wasn't easy. So we did both static analysis from the code, some dynamic measurements through changing the code, and to make sure that our findings are correct, we also implemented a complete user mode simulator that you can download and you can run even without the kernel itself. And of course, that was the best way to verify that our findings are correct. So that's about reverse engineering. Here's the structure of the Linux random number generator in short. I'll go from left to right. And then we will get into more details about each of these elements. First, entropy is collected. Entropy is collected from 4 sources. These are keyboard typings, mouse events, hard disk movements, and interrupts. All these are collected asynchronously, and I'll get back to it, and enter to a large pool. Then there are 2 additional pools. One is called the secondary, and the other one is called the urandom. One of them is used for the secured interface, and another for the less secure one. And as you can see, I guess that some of you can feel it. It's a bad coupling right now. The entropy comes from a single source, from a single big pool, which used to feed the other 2. It's in a bad way. All of these, what marked in single letters, the C, the A, the collection, the addition, the extraction, each of them is a different procedure, and I'm going to get to it in details. And you can see also the dashed line, which says that whenever you extract entropy, you also add a feedback back into the pool. So it's quite a complex structure. Lots of assembler operations per each random byte that you read. Okay, first about the collection. The collection is quite simple. I mentioned that it is asynchronously, meaning whenever there is entropy in the system, it is collected. Collected, gathered, entered into the pool. So whenever you move the mouse, type something on your keyboard, it is entered to your entropy pool, which is good. That's what we want to do. Whenever there is entropy, let's use it. I mentioned Windows, and I can tell you that our early results from the Windows operating systems prove that, for example, in Windows, they do not use it in this way. They collect entropy only whenever you extract, when you need random bytes. So that's a better way. Collect entropy whenever there is. So for each event, we collect 2 words, 232 bits of information. One of them is the event type, and the second is the timing in milliseconds of the event. So, for example, for keyboard, 32 bits for keyboard values, we don't need so many, right? How many do we need? 8. There are 256, that's it. No more than that. So some of it is redundant. Yeah, that's it. And for hard drive, if you have a single IDE drive in your machine, you get single value, fixed value, always the same. So there isn't much entropy coming from the event type. We actually do get a lot of entropy from the timing, from the millisecond of the event. That's where we get the entropy, the actual entropy. So the bad news is that the actual entropy in each event is very, very low because, as I mentioned, hard disk, almost none, keyboard, a little bit, mouse, there is some, and interrupts, by the way, are not implemented for all the devices. Interrupts are implemented just for certain device drivers in the operating system. So we get very few different values, but the good result is that we get a lot of them. Okay. Now to the math. I won't get into all the details, just to make sure that you get the picture. Each entropy addition, we take these values, the two 32-bit values, and add them to the pool. I'll go back. This is the addition is where you can see the letter A. So after we collect entropy, we do addition. That's on the entrance to the primary pool. When we add entropy to the secondary, again, we use the addition process. The addition process is a generalization of linear feedback shift register. It's a very simple mathematical operation. You can see it in the lower array. The G is actually the value coming from the operating system. That's the entropy, that's the noise, the 32-bit. And we XOR it with 5 different values from the pool and update another cell. So we take 5 values, the entropy, XOR it, multiply by some matrix, but that's not important, and enter it to one of the cells. That's entropy addition. Okay. How about extraction? Extraction is using SHA-1. And what we do, you can see here the pool that has 32 entries of pool. Each of them is a 32-bit entry. Okay? That's the smallest pool. So we do an iterative SHA-1 operation. First, we take the first half of the pool, hash it using SHA-1. Then we update one cell at I. Then we take the second part of the pool, hash it again using SHA-1 tag, and I'll say in a minute what's SHA-1 tag, and use it to update 2 additional cells. That's in I-1 and I-2. Then we do again SHA-1 tag and take the output, and from SHA we get 20 bytes of output, and the authors were afraid that someone will find an attack for SHA-1, that, by the way, is coming this year, and they added another layer of folding. So they take the 20 bytes and they fold it. They take 10 and 10 and XOR them into the result. And that's the output. So a very, very complex structure for the extraction of output from the pool. And again, as you could see, there are a lot of extraction. One when we read bytes from the dev random or from the dev U random, and whenever there isn't enough entropy in the small pools, in the secondary and the U random, we get additional entropy from the primary pool. Also, they didn't take the SHA-1 as is, but in the second and the third time, they used SHA-1 tag with no reason. They just changed the IV, the initialization vector, just like that. It took us a while to find out, but that, and I'm not sure why they did it. Okay, that's the extraction procedure.
The second line, I thought the SHA-1 is a fixed max output, right?
Mm-hmm.
But how did they fit into I?
It's a good one, good question. They just take the initial bits, the first 32 bits. You're right. The output of SHA-1 is 160 bits, and they take just the first 32 bits. Okay, so that's the extraction. And as you could see, it's a very, very complex structure. We have 3 different pools. We have entropy estimation. We have a collection asynchronously. We have addition using some complex generalization of linear feedback shift register. When you extract bytes, you do 3 SHA-1s, and when there isn't enough entropy, you extract from the first pool to the secondary with a feedback back, a very, very complex structure. Unfortunately, it's complex but not secure. First, I'm going to describe 3 attacks. Okay? The first one is theoretical, but it is very bad. I'm going to describe it in a minute. The theoretical result is very bad for the authors. The second is, and I guess that you could see it once you saw the description of the protocol, it is very easy to mount a denial of service attack. And I'm going to go into the details. And the third attack, as I mentioned, is a very practical one on a unique Linux distribution, OpenWRT. And you can guess, and in a few seconds, a few minutes, you'll see why. It's very easy to attack it. I'll give you a hint. It has to do with entropy or with the lack of entropy. Okay, so just the theoretical one first. As I mentioned, the entropy-based PRNGs, we want to have 3 properties: the backward security, forward security, and pseudo-randomness. We were able to mount an attack, again, mostly theoretical, on the Linux on its backward security, meaning my input is the state of the PRNG. I assume that you were able to break into a Linux machine, get the entire memory dump, and go away. Give me this memory dump. I have the entire state of the PRNG. And what you're going to see in the next slides, that I'm able to trace back past outputs of the PRNG. Yes? No. No. So the input of my attack is the state in stage N, and the output of my attack is the state in stage N-1, and of course also the output in state N-1. And I can run it for several times. Also, this attack is limited with the fact that I assume that during the attack there is no entropy addition during that time. Just to make sure that you see that it's not trivial, if you try a brute force attack, the number of operation is very large, that 2 in the power of 1024. That's impractical. And that's the number is the size of the pool, of course. So if you just want to do some brute force, you need to guess the entire pool state. But we can do much better. Actually, if we have the state, let's look at the extraction process. What we do in the extraction process, at each stage, we update 3 words. As you could see earlier, we updated 3 words. The word at index I minus 1, and I minus 2. So these 3 were updated. So if I want to do a brute force, a simpler brute force, all I need to do is guess these 3 words. So I'm going down from 2 in the power of 10, 24 to 2 in the power of 96. And that's, of course, much better. Again, as I said, it's mostly theoretic because 2 in the power of 96 isn't so practical today, but it's almost there. So that's very easy. And, of course, very easy also to understand it. And I can do it repeatedly. I can do it for one stage, for another stage, and I can go back and back. But there is some limitation. When we did it, we came into a problem. We call it the simulation problem, that we start with a single state, and we trace back. The green ones are the true values that we found. But because we are doing a complex combinatorial operation, we find, in addition to the true exact value, we find also imaginary ones. That's the yellow at the bottom. And we were afraid in the beginning that this will escalate very fast, exponentially. And we will have, after 2 or 3 stages, some huge number that you would say, okay, that's impractical. I cannot use it. Actually, and I won't get into the details, we did the combinatorial analysis and also some measurements, and the growth isn't exponential. The growth is linear. So after 100 stages, you'll have at most 100 imaginary values, which is, in security, is great. Very, very, very good result. How do I know after 100 stages how to take apart the imaginary ones? Let me skip, I'll skip the math. How do I know to solve the imaginary ones? I'm using the upper protocol. What's the upper protocol? Depends on your users. But let me remind you, we are using random number generators for some security application like SSL. So take each one of the 100 that you got from me and try using it on your encryption. If you get clear text that makes sense, that's the right one. Then you broke the security protocol. So that's the way to use it. That's the way to use the simulation problem. In some ways, in some cases, we were able even to mount a better attack than the 2 in the power of 96. In some cases, we were able to do it in 2 stages and break the 96 bits into 64 and 32, and then the attack becomes 2 in the power of 64. And that's, again, an advantage. And again, as I mentioned, that's a mainly theoretical result because first you need to break into a machine. Okay, that's sometimes practical. You need to get a dump of the memory, and then you need to compute 2 in the power of 64 or 2 in the power of 96, which is quite expensive. You probably won't use it. So that's mostly for the theoretical part of my talk. But as I mentioned in the beginning, when we are designing a security protocol or cryptography protocol, there is no reason that we'll have such flaws. And it's very easy to correct these, and I'll get back to it. Denial of service. Right now, there is no limitation on the using of dev random or dev urandom. So if I am a user on your machine, I can just open dev random and read. And of course, I'll finish all the entropy in the system, and your process, which may need just 4 bytes, may go to sleep forever. That's starvation in Unix, Linux. And that's very easy to implement, and there is no limitation on how many bits you can read. I can do it internally when I'm another process reading from dev random. I can do it internally when I'm another process reading from dev urandom, because both of them are using the same pool, the same main pool as I mentioned earlier. And I can do it even remotely, because some of the remote protocols are using random number generators from the system. One of them which we already mentioned is the TCP sequence numbers. But there are some more. For example, DNS. Again, SSL. So I can use all of them remotely to consume all your random bits, and you won't get any. That's starvation. And there is a very simple solution for that in operating systems, implementing a quota. And I hope that's one of our recommendations. And there are already discussions in the Linux kernel group of implementing quota for the random number generator. That's an easy way to handle such things. So that's denial of service attack. And as I mentioned, the theoretical attack becomes very practical in certain cases, and there are lots of Linux distributions. One of them is the OpenWRT. That's a Linux distribution for wireless routers, which implements SSL termination, SSH servers, wireless encryption, but it uses the same kernel. And the same kernel uses the same dev random. But I'm not sure about your wireless router. Mine, which looks like the one in the picture, has no keyboard, no mouse, no hard drive, and unfortunately, no interrupt is implemented. They could implement it, but unfortunately, the current version isn't implementing it. They should. So if there's, yes?
Is that because you said earlier that only some drivers have the
Exactly.
driver that's used on this device does not have it?
Exactly.
That means radio static, right? Like that?
Okay.
Radio static?
No. But after we suggested that and they started discussing it, but right now the stable version, the RC5, I think that's the last stable version, isn't using anything to add into it. So there is no entropy. No, they do not do anything. There is a flash operating system, but they do not use it for entropy. The only thing which they use is the uptime, the uptime of the machine to feed the entropy, which isn't good enough. And as someone already asked in the beginning, the Linux saves the state of the pseudo-random number generators between boots. So after you turn off your Linux machine, one of the last things that the operating system is doing is keeping some data from the dev random into a file, and whenever the machine gets up again, this data is fed back into the entropy-based PRNG, and is used to get entropy to the state, and that's a good mechanism. But nothing is going, there isn't anything going like that in the OpenWRT, unfortunately. So there isn't any state saving between reboot. So it's very, very easy to predict it. Our attack, just using our analysis, becomes very practical. I didn't want to publish a tool, but we were able to implement it and predict the entire output of the OpenWRT PRNG. And this is right for the last version. You could see that's a screen capture from my router from a couple of days ago. And the last version is White Russian 5. And it can also be mounted remotely. You don't need to get random numbers from the operating system. You can just, if you want to implement, if someone wants to implement this attack, you can just get one TCP packet from this machine, sync your simulator, find out the exact state of the OpenWRT, and that's it. You own the next output and the previous outputs of this PRNG, and any security protocol that uses this output is vulnerable. SSL, SSH, S-MIME. One last thing that we did, and that's just the beginning, is we did some kind of starting to do research on the entropy itself, because we believe, and we still need to prove it, that web servers or file systems, machines, will have a unique output for its entropy. It will repeat itself. And we did some measurements right now for running on a 2 weeks server, and we found very, very low entropy. That's the number below the 1.028. That's a very, very low entropy per each event. That's from an idle server, an idle Linux server running just file server operations. We were able to see that the actual entropy is very, very low. And again, that's just the beginning. I do hope that we will be able to find some more results on the behavior of the entropy itself. And again, you can see in the table that these are the upper levels, the upper values of each field, which should have been something like 32 bits, but unfortunately keyboard is 8 bits at most, mouse at most 12 bits, the hard drive at most 3 bits, but if you have, as most of us, single hard drive, that's a fixed value, and interrupt that just 4 bits. Per event. No, just per event. Okay, to conclude, what we found out and presented is the analysis of the Linux PRNG. If you're interested in the details, we also presented a much more detailed paper in the IEEE conference. That's a more mathematical one, and at the end of my talk there is the address of my website. You can download the detailed paper if you are interested to see the exact implementation details. Of course, our analysis is limited. Your own kernel may be different. You may change it. It's open source. Easily changeable. We didn't test our findings on unique machines with multi-CPUs, so it may be different, of course. And because there were so many patches, your exact version may vary, of course. Attacks, I mentioned one theoretic, some measurements, very simple denial of service, which hopefully will be fixed in the coming kernel versions. And you can see in the picture, that's the OpenWRT from inside. That's when you need to do hard reset. There's some way to open and use the flash for hard reset when you build the wrong version for the kernel. And unfortunately, that's vulnerable today. And hopefully, they will fix it. As someone mentioned, it's quite easy. They should add more entropy to the system. So fixing that's definitely a good step. Implementing the quota. If you are implementing a new entropy-based PRNG, as I suggested, do implement the Baraka-Levy construction. It's very simple to do so. And unfortunately, and as I said, I have nothing against open source, but I do think that open source can do much better for security. And saying that you can read the source isn't the solution. For example, going for different documentation system. The fact that anyone can add changes to the kernel, there is some signing mechanism, but the signing mechanism doesn't prove today any quality. There is no QA, there is no test vectors for any security part of the kernel that I know of. We have similar things for other protocols in cryptography, for example, and in security. We have test vectors for SHA-1, for ND5. Why can't we have some good examples for such protocols in the kernel? And I think that's definitely a good direction which open source can benefit from that. As I mentioned, you can find, I'll put the latest version of this presentation online. The one on the CD-ROM is a bit different. I added some slides, and you can find a detailed mathematical paper about our analysis on my web page, and I'll be happy to take any questions. No, we have. If you use we want all of them. Actually, we want to make sure that someone who gets random bits from a PRNG won't be able to predict the state. We want to make sure that once you break into the PRNG, you won't be able to know the past, and your ability to predict the future will be very limited till there is enough entropy. So we want all of them, and for the OpenWRT, you don't get any of them. For general Linux system, we were able to show that once you break in, you can predict the past. You can not predict the past, but you can learn about the past, and that's very bad. Think about banking system. Would you like that someone who breaks into the system can learn something about yesterday? Usually not, and it's true also for any commercial system. If the nonce is fixed, it won't be secured as well. Usually they take the nonce also for some kind of PRNG. Yes, please. Mm-hmm. Yes. Yeah, they'll pass it. And by the way, it's a good issue that you raised. the fact that we do have some statistical measurements for pseudo-random number generators, but unfortunately they can only prove that something passes them, but it's not proving anything about its security, of course. Yes, please.
You told us that this was to exist the entropy through the sending bits in a get. It's good to read the QoS, but each time the get is sent, there's an interrupt generated through the int count. So doesn't it refuse the...
As I mentioned, in some systems, yes, and some systems, no.
depending on the driver?
Exactly. I think that the last time I checked, if I'm not wrong, for example, the Intel card and the 3-Chrome cards were without interrupts. So, yes, please. Very dependent on the system. It depends how much noise is there in a system. If it's system, just a normal workstation has about an event per second, entropy event per second. That's a rough number from my trials. So that would give you, each such event is a 32-bit addition. Yes, please. It will solve half of the problem because it will avoid attacking someone by using the urandom to attack the random, but you still can consume as much as you can from the random, right? If you have separate change, yeah. It's internal, but I'm not sure if there are. I think that there are also remote protocols which uses the random, but I'm not sure there. Some people are using urandom instead of random just because of performance. That's your point? I agree. Any more questions? Yes, please. I'm trying on another mobile phone, yes, but I'm on my way. Yeah, it's maybe interesting. We are trying one of the other embedded Linuxes, but we just started with it. So hope I'll be able to publish something soon. Any more questions? Yes. I was able to predict the entire future bits of the PRNG. Which means that I know the next SSL key, for example. And as I mentioned, I didn't continue. I could use it For other things, I guess that for WPA as well, but I didn't try it. Okay, that's another direction. It just takes a lot of time. But as I mentioned, I can predict them very easily in a O of 1, 2 in the power of 10 to predict the entire output of the OpenWRT pseudo-random number generator. So I can predict any security protocol which uses that. Okay. Exact. Yeah. You completely match the... You get one key. You just need one key. You get the next key, and that's it. You can get as many keys as you like. Because the OpenWRT right now has no entropy, there is no way for the system to correct itself when I know the state. So that's it. Once I know the state, all futures till the next reboot of the router is predictable with no errors. Yeah. You mean this one? In more details? Let's take it offline. I guess that won't waste the others. Okay, thank you very much.